All right, today we're jumping into something really cool, a way to understand the very nature of science itself. We're going to be looking at agent-based models, which are basically virtual laboratories that let us study how science and discovery actually happen. So here's the big puzzle that gets this whole thing started. We know science works. It gives us incredibly reliable knowledge about the world. But scientists, they're human. They have ambitions, biases, they compete for credit. So how does a messy, social, kind of chaotic community like that end up producing something we can actually call truth? It feels like a paradox, and it's one that people have been trying to solve for ages.
To really get a handle on that paradox, we've got to break it down a little. Let's look at the key social puzzles that make science tick. The kind of stuff that's pretty much impossible to experiment with in the real world.
Okay, this is where it gets really interesting, because these are the core tensions. Take incentives. Are scientists just noble truth seekers, or are they driven by getting credit, getting their name on a big discovery? And could those selfish motives actually somehow be good for science? Then you've got communication. You'd think more is always better, right? But what if too much chatter just gets everyone to jump on the same idea too quickly? And what about the scientists themselves? Do you want a community where everyone is cautious and methodical? Or do you need to throw in a few wild cards, some risk-taking mavericks, to really push things forward? These are tough questions, and you can't exactly run a controlled experiment on the entire scientific community to find the answers.
So, if you can't run these experiments in a real lab with real people, where do you do it? Well, it turns out the answer is inside a computer, and this is where agent-based modeling, or ABM, comes into play.
So what in the world is an agent-based model? The easiest way to think about it is like a video game about science. You're not trying to model the whole system from the top down. Instead, you create these individual, little autonomous agents, in our case, virtual scientists. You give each of them some simple traits and rules about how they should behave, and then you just hit play and see what happens. The real magic is watching the emergent phenomena, these complex, totally surprising patterns that just emerge at the group level from all those simple individual choices.
Let's break that down. Step 1, you create your agents. Maybe you design one type of agent who's super cautious and another who's a total risk taker. Some might be well connected, talking to everyone, while others are more isolated. Step 2, you give them rules. The rules are always simple, local things. Like a rule might just be, hey, look at the research your neighbors are doing, and if it looks promising, go work on that. And step 3, you watch what emerges. You run the simulation, not once, but thousands of times, and you see what happens to the whole community. Do they find the best answer? Do they all get stuck on a bad idea? That's the discovery part.
This quote from Joshua Epstein just nails the entire philosophy behind this. The goal isn't just to look at a pattern and describe it. It's to see if you can generate it, to grow it from the bottom up. If your simple model, with its simple agents and simple rules, can actually create a complex pattern that looks like real scientific progress, well then you've just come up with a really powerful potential explanation for how it happens in the real world. Okay, so that's the how behind it all. Now for the really fun part, the what. What have these virtual labs actually found out? Let me tell you, the results are often completely counterintuitive.
Let's start with a big one, a real assumption buster. It just seems obvious, right? More communication between scientists has to be a good thing. Ideas spread faster, we correct errors quicker. But what the models suggest is, well, it's not nearly that simple.
And this brings us to something called the Zollman effect. So look at the left side. In a super connected community, info spreads like wildfire. That's great. But the downside? If the first bits of evidence are a little misleading, the whole group can lock on to the wrong answer way too early. They all convince each other, and that's that. Now look at the less connected community on the right. Here, you get what's called transient diversity. Different little clusters of scientists can explore different ideas for longer, without being influenced by everyone else. Yeah, it's slower to reach a consensus, but the big payoff is that the best theory has more time to gather evidence and win out. So, crazy as it sounds, a little bit of isolation can actually lead to a better result. It's this incredible trade-off between speed and accuracy.
To get our heads around the next big finding, we need this really cool metaphor, the epistemic landscape. Just picture a research topic as this huge, foggy landscape. All across this landscape, there are hills and mountains. The height of each peak represents how true or useful a scientific idea is, its epistemic significance. And the scientists? They're like explorers, all wandering around in the fog, trying to find the tallest mountain. So, in one of the most famous models using this idea, researchers populated the landscape with 3 kinds of virtual scientists. First, you've got your controls. These are the lone wolves. They just do their own thing and ignore everyone else.
Then you have the followers. They're more social. They see a neighbor climbing a promising-looking hill, and they head over to check it out. And finally, you've got the mavericks. These are the true contrarians. They actively avoid the crowded hills and instead go exploring totally new parts of the map, looking for peaks no one has even seen yet.
So, which community finds the highest peak? The results are just crystal clear. Groups that are cognitively diverse, the ones with a mix of types, always do better. And the communities with mavericks? They do way better. See, the followers are great at climbing a hill once it's been found, but it's the mavericks who are absolutely essential for discovering those big, new hills in the first place. They prevent the whole community from getting stuck on the first little hill they find and calling it a day. They make sure the whole landscape gets explored.
So right about now, you might be thinking, okay, this is all very interesting, but these are just simple cartoons, virtual scientists on a fake landscape. What can this really teach us about actual, complex human science? And you know what? That is an excellent question.
And the answer comes down to a core philosophy in modeling called the KISS principle. Keep it simple, stupid. The whole point is that these models are simple on purpose. The goal isn't to build a perfect one-to-one replica of the scientific world. That would be impossibly complex. The goal is to isolate just a few key variables to see how they interact and what they can produce. So let's just ask the question directly. What's the real value of these highly idealized toy models? What do they actually do for us? Look, these models are not crystal balls. They're not going to predict the next big scientific breakthrough. But what they do give us is incredibly valuable. For one, they provide how possibly explanations. They show us a plausible way that a phenomenon, like groupthink, could happen. They're also proofs of concept. They show us that it's at least theoretically possible for, say, less communication to lead to better results. You can think of them as superpowered thought experiments that force us to challenge our deepest assumptions. And maybe most importantly, they help us discover and isolate the potential engines, the causal mechanisms that drive group behavior, which we can then go look for out in the real world.
And this brings us right to the finish line, and maybe the most important point of all. Understanding these simulated worlds isn't just some abstract academic game. It has very real consequences for how we actually structure and fund science today.
The takeaways here are pretty huge. If mavericks are so critical for finding the best ideas, then maybe our funding agencies should have programs specifically designed to support that kind of high-risk out-there research. If being too connected can lead to groupthink, then how should we design our conferences or our research labs to get that perfect balance of communication and independent thought? These models show us that protecting cognitive diversity isn't just a nice-to-have, it's a strategic imperative for getting good results. And they give policymakers an amazing new tool, a way to simulate the potential impact of a new science policy before they roll it out in the real world.
So, in the end, all of this research forces us to think like designers. It poses this one giant question. If you could build a scientific community from the ground up, what rules would you give it to make it as effective as possible? The answers are definitely not simple, but these agent-based models give us a powerful, brand new kind of laboratory to start finding them.